test uses Scalable Vector Graphics, or SVG, for not only plotting states in different thermodynamic diagrams, but also for depicting a system or flow state, sometimes configuring a device or process graphically, and finally pie charts for mixtures. So I'll quickly give some examples of that. So I've already logged in and opened a few different tabs. See, here we have a few states calculated with a PC model, as you can see here. And you can see the state calculated is showing right here. If I go to state 2, you'll see the picture of the state. State 2 is like a mixture. It's a saturated mixture, and you can see the picture kind of depicts that. And state 3 is a superheated vapor for the PC model. The color of this dots inside changes based on the temperature. So in case the temperature changes drastic, those dots will become red. Also, if you go to the graphics panel, you'll find the calculated state depicted here. And also on top of that, on the side, you will find the saturation graph. So you can just copy and paste to reproduce the saturation graph, etc. So this graphics panel is going to expand. The work is underway. For instance, the constant pressure lines right now just produces some fixed constant pressure lines. Pretty soon you can be able to choose which state the line should pass through. And in addition to constant pressure line, you can do many other different kind of lines. You can change the diagram to different types of diagram, obviously, by just selecting here, and all other features that are kind of obvious to use, like flipping the axis, etc. Just to show you, here's a couple of flow states. You can see the flow states again is depicted like a flow, and as you go state 2, you can see the color of those dots changing, showing the temperature or pressure is different. Here, I want to also go to the device panel to show how easy it is to set up a device. So you can load, say, state 1. Notice that air is the fluid that is shown up here as soon as I choose that. So it's shown here. So it kind of keeps a tab on what you're doing. And that's how the device is loaded, because now we know the inlet and exit state. If you, for instance, know the heat transfer in this case, you can calculate other unknowns by solving mass energy and entropy equations. Other graphical usage can be found in more complicated devices, like this is a heat exchanger, multi-flow non-mixing. If it's a mixing flow or separating flow, then you can have 2 inlet and 2 exits. You can leave one of them blocked. By default, all of them are blocked. As you load state, the valve is open. So obviously, it can handle up to 2 inlets or 2 exits. But by cleverly using multiple devices, you can make a device. Suppose you put 2 devices back to back. The combined device can then have 3 inlets or 4 inlets as you like. For a process, this is a closed process. Similarly, you can see that you can load the beginning state and the final state. Or for that matter, suppose we have an open process, then you will notice, let me go and quickly launch an open process. This is the open process. Suppose we have a PC model. So here you will find that we should be able to not only load the beginning and final state, but also either the inlet or exit state. So this sort of graphics helps you to visualize the device or the process that you're analyzing, and make sure that you don't make simple mistakes while loading the states that are appropriately loaded. And finally, a mixture appears in many places, not just simple gas mixture, but also for combustion, equilibrium. So it works the same way the graphics work. Suppose we just compose the mixture, you can see it automatically is updating the pie chart. So in a complicated problem, probably a mixture is created as a product of combustion or equilibrium, and you can see its depiction in a pie chart with lots of details as you move the mouse over.